Welcome to the JCT Science second subject day. The theme for this day is Deepening the Learning. The recording of this series of screencasts was made necessary by the current situation, whereby the restrictions in place to counter the pandemic of COVID-19 has made it impossible for us to bring this workshop to teachers in its original format of a live workshop. We've made all possible efforts to adapt our workshop in such a way that, although it was originally designed for live interaction in groups, teachers can benefit from engaging remotely with its content. The video is broken into 4 sessions, which can be viewed separately. However, for continuity and in keeping with the day from last school year, it is recommended that you watch them in sequence. They are Session 1, Exploring Skill Development. Session 2, Planning. Session 3, Moving Students Forward. And Session 4, Exploring Concept Development. The video for each session will play from start to finish, and it can be stopped at any stage, rewound or rewatched. There are specific moments when we will recommend that you pause, engage with the learning experience, and then restart by pressing play. When this is the case, you will be directed to do so when you see the pause and play icons on the screen. This resource can be engaged with by individual teachers. However, some activities will be made richer by collaborating with colleagues, as happened during the workshop. With this in mind, we have endeavoured to bring you the teacher voice from the many cluster venues we visited throughout the country during the last school year. In order to do this, throughout the presentation, you will see a Blackboard slide, which will give you a flavour of some of the conversations that occurred and feedback from the teachers. Before we begin, here are a few housekeeping points to note. Please open the booklet that accompanies this video. It can be found adjacent to the video you are viewing on the JCT website. It can be viewed online or downloaded or printed off. If you need some scribble space, I would recommend that you keep a small notepad and pen on your desk. You might also like to have some highlighters. You will be invited to use a QR code reader to access material throughout the day whenever you see a QR code on screen or in the booklet. If you don't have one on your phone, it might be worth downloading one now. They are generally free. This is session 4 of the 4-part series of screencasts for the second subject science cluster day. In this part of the day, we will explore energy as a concept and consider the challenges involved in teaching concepts in science in general. Before we get into this part of the day, let's recap on the learning intentions of the day. Here are the learning intentions for the day. To deepen our understanding of the process of developing our students as scientists. To appreciate the value of collaborative practice in our department. We will now explore the difficulties in teaching science concepts, using the example of the concept of energy. The abstract nature and language struggles associated with teaching concepts in general will be established. Some pedagogical approaches are suggested to help tackle the common struggles identified in this session. Let's get straight into some junior cycle science. Think about what you see in this word equation on the slide. Now use these following framewords to think about the word equation. Energy, the law of conservation of energy, and energy cannot be created. If helpful, write down the word equation and the 3 framewords. Pause here now to record your thoughts about the word equation and the framewords on the slide. The definitions given here describe a concept as an English word and a scientific meaning. A scientific concept's definition shows it's more complex and specific in meaning than its general English language meaning. Let's explore one science concept in junior cycle science, the concept of energy. In a moment, pause the video to read the quote on the slide from Richard Feynman, a Nobel Prize-winning scientist, and take a moment to reflect on what the quote means to you. Does the quote make sense to you? Note the date of the quote. Is the quote still relevant today? The purpose of the quote here is to highlight the complex nature of science concepts. They are abstract and often mathematical. This is the case for the concept of energy, as referred to in the quote by Feynman. The quote suggests that energy is a most abstract idea that can be made tangible using mathematical principle or numerical quantity, based on energy being a conserved quantity. Now consider, how do you teach a concept like energy? In the past, when we asked students what energy is, the definition on the next slide is what they were taught to give us. Let's now consider how this definition holds up in terms of developing a deeper understanding of the concept of energy and laying down foundations for future learning. Energy is the ability to do work. What do you think of this as a definition for energy, or as a statement about energy? Would most students have offered this as the answer to the question, what is energy? Let's dig a little deeper into the importance of laying strong foundations in science concepts for students and how this can impact future learning. Firstly, what does the Junior Cycle Science specification say about teaching concepts? The Junior Cycle Science specification says the following about teaching concepts. It is recognised that the skills, knowledge and understanding of the scientific concepts, as set out in the learning outcomes, take time to develop and often need to be carefully revisited and reinforced. Note that it is the concept that would need revisiting and reinforcing, and not individual learning outcomes. If energy is an abstract idea, how can you make it something students can access? Let's now explore some of the pedagogical options we could use. One approach you could take for teaching science concepts is the use of analogies. Reflect for a moment on the purpose of an analogy as a pedagogical tool in learning. Analogies can help students make meaning of difficult abstract concepts by using a comparison with a common tangible thing. Have you used any analogies before in your teaching? How do they help in achieving the intended learning? We are now going to have a look at using money as an analogy for energy. Let's use the booklet here now. Go to pages 26 and 27. The booklet uses icons to indicate how you should engage with the activities, either as a student or a teacher. The school bag icon indicates the activity is designed to be completed as a student. The icon, the teacher at the whiteboard, indicates completing the activity as a teacher. The purpose of this activity is to guide students' thinking to make connections between the language used about money and how these words might transfer to understanding energy. These words become the mapping words. You can then use the table on page 27 to record your mapping words for money and energy. Now let's have a go at the activity on page 26, the student worksheet, from a student's perspective, keeping energy in your mind, and then complete the mapping activity on page 27. Let's review the activity you just engaged in. The Blackboard slide will now show feedback from science teachers across the country during last school year's cluster day. Common mapping words that arose for money as an analogy for energy were stored, transferred, invisible, conserved, measurable. Did you have any of these mapping words, or any different ones? One of the strengths of an analogy is that there are lots of mapping words or points that show similarities between the tangible analogy and the abstract concept. Pause here now for a moment to record your own thinking. Let's discuss the limitations of analogies now. All analogies have limitations. Identifying these limitations through discussion is a valuable part of learning and understanding for students, as well as providing a fail-safe space for students about possible misconceptions they may have. What are the limitations of this analogy? Use the space at the bottom of page 27 to record your thoughts. Pause here now to allow for your recording. The Blackboard slide shows feedback from the last school year's cluster day about the limitations of using money as an analogy for energy. Common limitations that arose in the rooms were as follows: inflation, the printing of money, that the value of money can change, that money can be damaged, and that money can exist negatively. Did you come up with any other ones? The use of analogies can help bring about conceptual change for students. It is important to decide if an analogy is suitable for the concept. The slide here identifies the pedagogical benefits of using analogies. Analogies have the potential to be a powerful tool for deepening learning through using a tangible, commonplace, alternative learning experience for students. A good analogy is where there is explicit mapping to the concept and enough alignment between the abstract concept and the tangible analogy that can help move the learning towards understanding. If an analogy can be built upon, it is more valuable. A good analogy allows the learner to form a bridge between the real and the abstract, to allow for meaning making to happen for the student. Identifying the limitations of an analogy is important to avoid an analogy leading to misconceptions. The process of getting students to identify the limitations of an analogy can also help students see inconsistencies in their own conceptions compared with formal science beliefs. This can then lead to dissatisfaction for a student about their own thinking about a concept, and then lead to conceptual change for individual students. So analogies can help bring students to checking their own current understanding about a concept and help avoid as well as identify misconceptions in their own thinking in a fail-safe space. An analogy is one way of teaching concepts. Let's look at another way, using simulations. Let's now consider the potential of simulations as a pedagogical tool to help teach concepts, in particular the concept of energy. We will explore the simulation Energy Skatepark Basics from the PhET Simulation website. We will look at the value of this PhET simulation in deepening student learning about concepts. The money analogy introduces students to the concept of energy through language mapping. Let us now investigate what are the key features of energy that the PhET Simulation app enables, that enhances student learning, as well as what are the limitations. Go to page 28 in your booklet. Use the QR code on the top of the page, also shown here on the screen, to open the Energy Skatepark Basics simulation. Alternatively, use the URL in the booklet also to access the website. The image here on the screen shows what the simulation looks like. Before you pause to play with the simulation, here are some suggestions about engaging with the activity. Spend 5 minutes to explore the play features of the simulation, and then consider the benefits and limitations for learning for students about the concept of energy. Use the worksheets on pages 28 to 30 to support your investigations of the learning potential of this pedagogical tool. A reminder also about the icons for engaging with the activities and worksheets. For the initial parts of the worksheets, you will be engaging with it as a student. And then for other parts, you will engage with questions and discussion activities in the worksheets as a teacher. Pause here now and have a go. Now that you've had a look at the activity, what do you think are the strengths and limitations of this simulation in helping students understand about the concept of energy? The next Blackboard slide gives feedback from science teachers who attended last school year's cluster day from across the country about the strengths and limitations of the simulation. Based on feedback from science teachers who participated in last school year's cluster day, the Blackboard slide here shows strengths and limitations that were identified in the use of simulations to teach concepts. Pause here now to take a moment to read. Did your ones come up? So we've explored two pedagogical tools, the use of analogies and simulations, to help teach science concepts, like the concept of energy. Digital tools have many features that can enhance concept development, like the instant feedback features and resetting features that can be seen in the simulation tool. They can help with finding out where your students are in their learning and what aspects of learning and understanding about the concept need clarification for individual students. This aligns with the science specification recommendation about teaching concepts, which requires revisiting and reinforcing. Note that this is not reteaching of the same material in the same way, as students are continually learning. The use of any digital tools should always be for enhancing learning and not just for the sake of technology. How do pedagogical tools help deepen learning? In the classroom as teachers, we are very comfortable with carrying out investigations and of the benefits they allow for student learning, for example, providing inquiry-based learning experiences. In previous science cluster days, we explored the use of models as a pedagogical tool as a means of representation that give learners a different way of acquiring information and knowledge about obscure objects. In this cluster day, we are exploring analogies and simulations. There are many pedagogical choices available, and it is our job to choose what is most valuable for our students' learning at a point in their learning. It is important that we are thinking of the when and why we are using different approaches. Do simulations offer opportunity to deepen understanding for students about the concept of energy? For example, let's explore the Energy Skatepark Basic simulation a little further about this. Do simulations offer opportunity to deepen understanding for students about the concept of energy? Let's look a little more closely at the skatepark simulation. In the Energy Skatepark Basic simulation, we can see there are different options available that can help with understanding about factors that affect energy, like friction. There is a non-friction world in the intro option. There's a friction world option, and then there is a playground option, which collectively provides scaffolded learning opportunities for students. Let's explore the different options here now. Firstly, the non-friction option helps students understand about the law of conservation of energy, represented by the bar chart exchanges, where energy transfer is clearly seen between the potential and kinetic bars as the skater moves on the ramp, and that the sum of these two bars is always equal to the total energy bar. At all times, it is clear to see that the total energy of the system is equal to the sum of the potential and kinetic bars, where the system is the skater moving up and down the ramp. This is a visual representation of the law of conservation of energy. Secondly, the friction option allows for comparison with the non-friction option to help deepen understanding about an important aspect of energy, the dissipation of energy. This can be seen in the slide here in the friction world option, where the skater slows down to a stop. As this slowing down is happening, an increasing energy transfer is evident in the thermal bar until all the energy is transferred to the thermal bar, representing that the skater has stopped. The same energy transfer to the thermal bar continues to be seen in this L-shaped ramp version, as seen on the slide here, even when the skater goes off the screen during play. But this is not the case in the non-friction world, where the skater never slows down, but moves with continuous motion, more easily seen in the U-shaped ramp here, and where no energy transfer is seen to the thermal bar. The different versions of simulation play offers the opportunity for students to make inferences and predictions about the skater's movement, using patterns from the bars in the bar chart, and to connect this to the energy change happening in the system. So, what valuable learning is there for this for students? In the non-friction world, on the slide here, students can see that there is no energy transfer to the thermal bar, only between the potential and kinetic bars. This allows students to make inferences about the data from the bar chart and to try make sense of it by connecting this data to the frictionless world. Similarly, students can see that in the friction world that it shows energy moving between all three bars, the potential, kinetic and thermal, and that the skater moves differently. The opportunity here for making inferences and predicting the skater's movement, as well as gathering energy profiling data, provides richer and deeper learning experiences for the more able students. Thermal energy is dissipated energy. Let's clarify our thinking on what dissipation is. In terms of understanding about the concept of energy, in this simulation, the thermal bar represents dissipated energy from the system. The connection in learning here is that energy is always dissipated from systems in different forms, but mostly as heat energy. Hence, the use of the word thermal here for the bar representing dissipated energy. The system in this case is the skater moving up and down the ramp. Let's take a moment now to think about dissipation as part of the concept of energy. Understanding dissipation can be helped with the following statements. To know that no system is perfect. Whenever there is a change in a system, energy is transferred and some of that energy is dissipated. The total amount of energy is always the same before and after a process. Some of the energy is now more spread out and less useful for doing things with in the future. Reflect on how the statements here might help deepen understanding about dissipation and the concept of energy. Let's revisit the money analogy. How can the money analogy help deepen learning about dissipation as part of the concept of energy? Thinking in terms of money, if you had a €1 coin and you gave it to a student going into a shop, the student can make use of it. Whereas if you gave 100 students a 1-cent coin each individually, they cannot make use of that money in the shop. A 1-cent coin is less useful than a €1 coin to buy stuff, in the same way as dissipated energy is less useful to do stuff. This is an example of how an analogy can be built upon to further deepen student learning, and in this case about energy and dissipation. The next slide gives advice about teaching the concept of energy. The advice here for best practice when teaching the concept of energy is, if the law of conservation of energy is to be upheld in our teaching, energy dissipation and energy changes should be taught simultaneously. Dissipation is inevitable in all systems in the real world. Therefore, it is vital that dissipation is considered at the same time when talking about energy changes. Just as we've seen in the simulation, if we ignored the thermal energy, we teach an unrealistic account of energy in nature. We looked at using analogies and simulations to deepen learning about the concept of energy. Another important fundamental aspect of learning is language itself. Let's take a moment to read the quote here from Wellington and Osborne about language use in science. Many of the hard conceptual words have a precise meaning in science, and sometimes an exact definition, but very different meaning in everyday life. The quote here draws attention to the importance of how we use words as part of language in science. If we take energy as our example and consider how everyday language uses the word energy in a lot of different contexts, which have wide variations in meaning, and think how this impacts on teaching and learning, especially how it affects our students' understanding. In science, language is significant in terms of the precision of meaning required with words, especially words that have multiple meanings in the English language already and are commonly used in everyday conversation. Let's look at some examples of this. For example, when your students talk about energy in everyday life, what do they say? What kind of terms do they use? Let's look at some common terms using the word energy that do not have an accurate science meaning. Positive energy. I've run out of energy. They are full of energy. Save energy. The speech bubbles here guide us that the law of conservation of energy gives us a different meaning to what these common terms have suggested. Students often hear about saving or conserving energy and often associate energy as an exhaustible quantity. But in scientific terms, it is not energy that is used up, but the fuel or food as the source of energy that needs to be conserved. By thinking energy can be used up can cause issues in the future for students' learning. Thinking of this and looking at other areas of science where language or concepts can be muddled in students' heads, take a moment to think, what are other common words or concepts that students confuse? Based on feedback from science teachers who participated in last school year's Cluster Day, the Blackboard slide here shows some of the commonly confused terms or concepts in science. Pause here now to read. Did any of yours come up here? When we are speaking scientifically with our students, we need consistency of language. Research has shown that it is very important to build on the students' commonplace language to avoid them dismissing new language and thinking. We need to make the new language so commonly used that they become comfortable in using it in their vocabulary. If we dismiss their commonplace language, it can lead students to further separate the science in the classroom and the science in their everyday lives. We must also take care with how we use language with our students, particularly with concepts like energy, which needs to be carefully constructed in our students' minds. If the new words or language is not accessible to them, they will revert back to existing conceptions or misconceptions. We have explored the importance of laying strong foundations in science concepts for students to future-proof their learning. We also considered what is important when planning how best to teach concepts and making effective use of the pedagogical tools available. In this session, we explored teaching concepts as part of the journey in how we can develop our students as scientists. The journey is never a linear path, which is a reminder to us about the unique journey every student takes in their own school context, and of the importance of this journey as a process that helps us reach a common goal. We have considered how to teach concepts, in particular the concept of energy, as part of the science specification at junior cycle. We touched on what is important in planning how to teach concepts in science, in terms of pedagogical tools that can support deeper learning of the concept of energy. This slide here shows that the pedagogical planning we engaged in forms part of the bigger picture of planning, required at a subject department level, to ensure that a cohesive and progressive plan is structured collaboratively, that reflects the context of the school and provides enjoyable, rich, accessible learning experiences for all its students. This reflects the aims of the science specification. The slide here shows the number of platforms on which you can contact us. This information is also on page 35 of the booklet. Use the JCT registration link to offer feedback when you have completed all 4 of the sessions. Finally, this recorded session is one of 4 parts of this series of screencasts, a digitised version of the Cluster Day Deepening the Learning, put together by the JCT Science team due to the restrictions to counter the pandemic of COVID-19. To get the most from the day and a more complete understanding of the learning intentions, you should engage with all parts of the day in the suggested order given at the start of this session. Thank you for your engagement.